So in this video, we have a particle moving at a constant speed between 2 points, and we want to find the parametric equations if the speed of the particle is 5 units per second. So we're given the speed in this case. So what we might want to think about is, what does our velocity vector look like? Well, it's a constant speed, so our velocity vector would be made up of constants, and basically it would be the vector between the 2 points. So our velocity vector would be the vector PQ, and to find the vector PQ, we just take the difference of corresponding pieces. So 5 minus 2, it's always the ending minus the beginning, because we're going from P to Q, we're increasing 3 in the x direction. So that's why we do 5 minus 2. 3 minus a negative 1, and negative 1 minus 5. So this vector, our velocity vector, we can call it, is going to be 3, 4, minus 6. Okay, now we're going to need the magnitude of this velocity vector, as we need it to have we need to know what the current speed is so we can make sure that it has a speed of 5. So to do the magnitude, we do the square root of the sum of the squares of the components. So we are going to have the square root of 9 plus 16 plus 36, which, let's just keep it as a square root. We'll keep it nice and exact. We can always change it at the end. So square root of 61. Now, I wanted the magnitude of the velocity to be 5. So what I'm going to do is I'm going to make the velocity vector a unit vector. So this new vector, let's call it W, is going to be 5 over square root of 61 times our original PQ vector. Now let's talk about this for just a sec. We're dividing by the magnitude. That makes it a unit vector. Then multiplying by 5 guarantees us that we have a magnitude of 5. So we know that the magnitude of this vector W is 5. So basically what we're going to do now is the antiderivative of this. So when I'm going to find R, the position vector, it's the antiderivative of W, which would be some initial position, x0, y0, z0, plus, basically these are all constants, so I would just add in a t, and I'm just going to add it out front, 5t over square root of 61 times 3, 4, negative 6. Now, we haven't really said at when we're going to be at what point, so probably the easiest is just to say, how about at t equals 0, let's be at point P. Because what that does, if t is 0, this all cancels out, and so my initial position is actually just the point P. So that'll allow my vector R to be 2 minus 1, 5, plus 5t over square root of 61 times the vector 3, 4, negative 6. So this will meet all of our requirements. Now, we could write this as x of t, y of t, z of t. And so what that would look like, let's just put them over here so that we have them. X of t would be 2 plus 5t over rad 61 times 3. So maybe we'd write it as 15t over square root of 61. Y of t is going to be starting at negative 1. And so 4 times 5 is 20. So we're going to have 20t over square root of 61. And finally, we've got z of t, which is starting at 5. And going to end at negative 6 times 5, which is negative 30 t over square root of 61. And if we wanted, we could have just made it 5 minus. So let's just do that. 5 minus 30t over square root of 61. Now, Let's make this thing end at point Q, because we do need to give a t range for this. Well, we know that we're starting at 0, and we can see that pretty clearly because 0 is going to cancel all those out, which would put us at 2, negative 1, 5, which is point P. We want it to end at Q, 5, 3, negative 1. Well, remember what we did to our vector PQ in order to make it have a magnitude of 5. We multiplied by 5 over rad 61. So to undo that, we just have to multiply by the reciprocal. So square root of 61 over 5 will make sure that we end at point Q. If we don't see that right away, imagine multiplying, for instance, x of t by rad 61 over 5. The rad 61s would cancel. We'd have 15 over 5, which is 3. 2 plus 3 is going to end us at 5. And it's going to be the same for the other two coordinates.